In the early days, mathematicians were fascinated by the various curves that they saw in nature and studied their geometrical properties. Often during their study, they found practical applications of these curves. The Greek mathematician Apollonius studied the various conic sections in the 3rd century B.C. You know that ellipse, hyperbola, parabola are all examples of conic sections. After Apollonius studied these conic sections, they were found useful in many ways. But the real breakthrough in the study of curves came with the work of Descartes. His work had the effect of unifying elementary mathematics, which was till then divided into two separate compartments, algebra and geometry. Descartes introduced the technique of visualizing geometric shapes as equations and equations as geometric shapes. If we look back, we find that most of the early developments in calculus were motivated by geometric considerations. Now in the study of curves, we can have two approaches. One is the pictorial or geometric approach, and the other is the analytical one. In this program, we shall bring out the interplay between these two approaches. For this, we'll take a look at a number of known curves and study their geometrical features. For example, take this curve. It is symmetric about the y-axis. But this curve is not symmetric about the y-axis. But you can see that it is monotonically increasing, whereas this curve decreases in the first quadrant. You can also see that this curve has a maximum at this point. We have made all these observations about symmetry, monotonicity and maximum values by looking at the graphs. But we could have noted these very features by just studying the equations to these curves. Let's take these features one by one and see how we can study them through equations. Let's start with symmetry. We don't have to go very far. The human body itself is symmetric about this vertical line. So naturally, when a tailor cuts the cloth, he uses the symmetry of the human body to his advantage. We see many examples of symmetry all around us. But now let us talk about symmetrical graphs. Here is a graph which is symmetric about this line, the y-axis. This circle here is symmetric about the y-axis and also about the x-axis. And what about this graph? It is symmetric about the line y equal to x, but it is not symmetric about any of the axes. Now suppose we have not shown any of these graphs and we are given only the equations to these curves. Y equal to x square plus y square is equal to a square, y equal to 1 by x. How can we decide their symmetry? Easy. Look at each equation. If it has all even powers of x, then it has to be symmetric about the y-axis. So you see, these two are symmetric about the y-axis, but this one is not. In the same way, if the equation has all even powers of y, then it has to be symmetric about the x-axis. So here you see, this and this are not symmetric about the x-axis, while this one is symmetric about the x-axis. We can also check the symmetry about the line y equal to x. Just interchange x and y in the equation. If you get an equivalent equation, then the curve is symmetric about the line y equal to x. You can see that the curves represented by these two equations are symmetric about the line y equal to x, whereas the curve represented by this equation is not. Now for the symmetry about the origin. Replace x by minus x and y by minus y. If you get an equivalent equation, then you can be sure that the curve is symmetrical about the origin. Here these two curves are symmetrical about the origin, but this one is not. So we have seen how to check the symmetry from the given equation. Let's move on to the next feature now. Monotonicity, rising or falling curves. Look at this graph of y equal to sin x. As we move from 0 to pi by 2, this graph keeps rising. Then as we move from pi by 2 to 3 pi by 2, the graph falls. It again starts rising as we move from 3 pi by 2 to 5 pi by 2. But remember one thing, to see whether a graph rises or falls, you should move only from left to right and not in the opposite direction, because left to right is the direction in which x increases. Now what about this curve? It falls till it reaches so and then rises. We could also say that it falls for negative values of x and rises for positive values of x. Again, if we are given only the equation, we'll have to check the sign of the derivative to decide whether the graph rises or falls. If dy by dx is positive at a point A, it means that the graph rises in the neighborhood of A. On the other hand, if dy by dx is negative at a point B, then it means that the graph falls in the neighborhood of B. Take y equal to sin x. Then dy by dx is equal to cos x. Now cos x is positive if x lies between 0 and pi by 2, or if x lies between 3 pi by 2 and 5 pi by 2, and so on. You can see that these are exactly the intervals where the graph of sin x rises. If we take y equal to x square, then dy by dx is equal to 2x. Now 2x will be positive if x is positive. That is, the graph rises if x is positive. Again, 2x is negative if x is negative. This means the graph falls if x is negative. As you know, dy by dx gives us the slope of the tangent to the curve. If we consider a curve as the path traced by a moving particle, then the tangent at any point gives the direction of motion of that particle at that point. We have been talking about rising and falling graphs. So here the graph rises and here it falls. But what about this point? To the left of this point, the graph rises, and to the right of this point, the graph falls. This point looks like the tip of a hillock. Similarly, this point resembles a valley bottom. A jump from one extreme point to another. The hillock tip represents a maximum and the valley bottom represents a minimum. If we want to be very precise, we call these the local maximum and the local minimum. That is, this point represents a function value which is greater than its neighboring function values. And similarly, the local minimum represents a function value which is less than its neighboring function values. If we study the tangents around the maximum, we find that the slope of a tangent to the left of the maximum value is positive. The slope of the tangent at a nearby point on the right is negative. And at the maximum itself, the tangent is horizontal. That is, its slope is 0. Now we can very easily draw up the algebraic analog of the situation. To check whether a point on the curve is a maximum or not, we look at the sign of dy by dx in a neighborhood of that point. dy by dx greater than 0 for x less than x0, dy by dx at x equal to x0 is equal to 0, and dy by dx less than 0 for x greater than x0 imply that x0 y0 is a maximum. On the same lines, we can write the criteria for a minimum point. The three conditions dy by dx less than 0 for x less than x1, dy by dx at x equal to x1 is equal to 0, and dy by dx greater than 0 for x greater than x1 imply that x1 y1 is a minimum. Now these conditions mean that the sign of dy by dx changes from negative to positive while passing through the minimum. Or we could also say that dy by dx increases while passing through the minimum. This can be ensured if the derivative of dy by dx, that is d2y by dx square, is positive at the point. Then we can replace the earlier conditions for the minimum point by another set of conditions. dy by dx at x equal to x1 is equal to 0, d2y by dx square at x equal to x1 is greater than 0 imply that x1 y1 is a minimum. Similarly, we get this set of conditions for a maximum point. dy by dx at x equal to x0 is equal to 0, and d2y by dx square at x equal to x0 is less than 0 imply that x0 y0 is a maximum. So to find maxima or minima, we first find the points at which the first derivative is 0 and then check the sign of the second derivative at those points. Now let's turn our attention to another geometrical feature of curves, concavity. While drawing curves, we are told to plot as many points as we can and then join them by a smooth curve. But there are many ways in which we can join 2 points. For example, A and B can be joined like this, like this, like this, or even like this. Let's take these one by one. In the first case, the portion of the curve is called concave downward. You will see that if we draw a tangent at any point in this portion of the curve, then it will lie above the curve. In the second case, we have a concave upward curve. A tangent drawn at any point here will be below the curve. Here is a simple way to remember the upward or downward concavity. Imagine that you are riding a bicycle along the curve from left to right. If you take a left turn, it means the curve is concave upward in that neighborhood. If you take a right turn, it means the curve is concave downward around that point. You can also study the third and fourth cases. In these cases, the curve is concave upward in one part and concave downward in the other. The upward or downward concavity of a curve around a point can also be decided by looking at the second derivative of its function. The first of these cases, when the curve is concave downward, is indicated by a negative second derivative. A concave upward curve is given by a positive second derivative. In the third case, we find that the curve is concave upward between A and C and concave downward between C and B. Between A and C, the second derivative is positive. Between C and B, it is negative, and it vanishes at C. We just reverse the signs and get the fourth case now. So here d2y by dx square is negative between A and C. d2y by dx square is positive between C and B, and it vanishes at C. In these two cases, we see that the curve changes its concavity at the point C. Such a point on the curve is called its point of inflection. Till now, we have discussed the symmetry, monotonicity, maxima, minima, and the concavity of a curve. Now let's take one last feature, the asymptotes of a curve. Here we shall consider only those asymptotes which are parallel to the x-axis or to the y-axis. Asymptotes indicate the tendency of a curve far away from the origin. Look at these two curves. The first one is given by the equation y equal to 1 by x, and the second one is given by y equal to tan x. Let's look at the first one in detail. What happens as x goes on increasing? You can see that the curve comes nearer and nearer to the x-axis. Similarly, as y takes larger and larger values, the curve comes nearer and nearer to the y-axis. Thus, both x and y-axis are asymptotes of this curve. Take this graph of y equal to tan x now. Here you will see that the value of the y coordinate of a point on the curve becomes bigger and bigger as its x coordinate approaches pi by 2. That is, the distance between the curve and the line x equal to pi by 2 goes on decreasing. The line x equal to pi by 2 is an asymptote of this curve. Similarly, x equal to minus pi by 2 is also an asymptote. We have a very simple way of finding the asymptotes of a curve governed by a polynomial equation in x and y. That is, an equation of the type fxy equal to 0, where fxy is a polynomial in x and y. Now, to find an asymptote parallel to the x-axis, we have to take the coefficient of the highest power in x and equate it to 0, and then solve this equation for y. The solution then gives us the asymptotes parallel to the x-axis. For example, take the curve y equal to 1 by x. We can also write this as xy equal to 1. The highest power of x here is 1, and the coefficient of x raised to 1 is y. So y equal to 0 gives us the asymptote of this curve, which is parallel to the x-axis. Similarly, to find the asymptotes parallel to the y-axis, we take the coefficient of the highest power in y and equate it to 0, and then solve this equation for x. For example, take the equation to the curve xy square minus 2y square minus 4x is equal to 0. We can write this equation as x minus 2 into y square minus 4x is equal to 0. Here, the highest power of y is 2, and the coefficient of y square is x minus 2. So, we'll equate x minus 2 to 0 and get x is equal to 2. Then x is equal to 2 gives us the asymptote of the curve, which is parallel to the y-axis. Till now, we have discussed various features of curves. We have talked about the symmetry of curves, their concavity, points of maxima and minima, and also the asymptotes of some curves. Side by side, we have also seen how to infer about these features when we don't have the graph in front of us, but only have the equation. These considerations are also very useful when we want to draw a curve given by an equation. Then, our main task is to analyze the given equation. We find out dy by dx and d2y by dx square and try to get all possible information about the curve, its symmetry, its tangents, its points of maxima and minima, its concavity, and also its asymptotes. All this information will give us a clear idea about the shape of the curve. Now, when you see various curves of different shapes around you, try to note all their geometrical features, and then also try to think about the conditions governing the equations of these curves.